questions. I'm stoked with what I was hearing as I was walking around. Even though Cassidy scared me telling it, we don't talk to Katie back there. But anyway, here's the data. Well, you have the raw data in front of you, the raw-ish data. Here's the summary data in box plot form. The reason I gave you the raw data plus the summary data in box plot form was twofold. Number one, any unusual values? Nothing apparently. You'd want to be careful if you had, say, large core plus outliers over here, because then you might artificially be pulling your average. So it might look like an average is higher, but it's actually only higher because of outlier data. The old Larry Bird thing. So it looks like everything's fine. It's just normally distributed data, roughly normally distributed data that's not behaving in any outlierish, outlandish fashion. So, who looks like they're doing better? So it looks like Core Plus is doing better by the box plot. Descriptively, Core Plus is doing better. Now does it hold up to inferential analysis? That's the whole point of the problem. Good. We already have our variables defined from last time, which is fantastic. Perfect. All we got to do is make sure this is correct. And I want to come back to something I heard Blake, Alan, and Naomi talking about, and I love the discussion I heard about this. What are these going to look like? What's the research going to be if we're trying to test what you guys just said? That's what we're trying to see, yes? If Core Plus is doing better, Core Plus's mu1 is doing better than traditional. It's the exact opposite hypothesis from last time. Emily, ask that question.
Why?
Oh, why? That's a good three-word question. Why? Who wants to answer it for? Why is it not the other way?
I would assume that you're testing the same thing, but with calculators.
You are, but what is... Remember how last time, Em, if you will, Emily, I'm going to put the old data back up. Watch where those box plots are. I wish I could put all four up at once, but the TI won't let me. That's the new data. Here's the old data. L2, that's Core Plus without calculators. Here's Core Plus, here's traditional without calculators, okay? Oh, hang on. L2, I thought I took L2, didn't I? I'm supposed to positive I did. There. That's the old data. That's without calculators. How's Core Plus look like they're stacking up there? They look like they're doing worse, yes? That's Core Plus on top, traditional on the bottom. Looks like Core. So that's the test we just did together on the first template. But when we gave them calculators back, different groups of kids, different control, different experimental, you see what happened? There's Core Plus with technology. Here is traditional with technology. You see what happened? Core Plus shifted ahead. Now the question is it inferentially better? Is it statistically significantly higher? Is that fair? Now, Emily, your frustration is well felt because if you weren't sitting in this class having this discussion, it might be confusing as to what to do. That's why when you do the quizzes out of class, the stuff for the project in week 10, the stuff for the last exam, I tell you what to test. Test to see if they're doing better, test to see if they're doing worse, and test to see if they're different. And so, is that fair? Maybe a little bit.
So we're not going to have to draw the box plot?
Oh no, the box plot is something I'm putting in your brain now for when you're researchers. You want to make sure your data is not completely skewed. And I mean skewed in statistical terms, because then if the Core Plus kids look like that, but they had wicked outliers, and you do an average, you might just get an outlier that's pulling to the right unnecessarily. I like doing the box plots just because it's like, okay, let's make sure the data is actually legitimate. Yeah.
What do you do with that outlier?
And that's a good question. You research it more. You find out why it's an outlier if you can. It might be that particular data point was measured differently, or that particular outlier is representative of the population, but a random, and that's something that goes beyond the scope of like what we know about. You have to know how those kids test, how those kids learn. It's a bigger question than just throw it away or leave it in. But the question is, should you leave it in? If it's considered an acceptable representative piece of the population, leave it in, because it should have an equal weight in the population. If it's not, then you have to dump it to be able to justify why you dumped it. Is that fair? It's a little more of a research methods question than a logistics question. But as far as outliers go, I like testing for them because if they're there, the reason I bring this up, related to 243, and you weren't my 243, I read a paper in 243 about energy drinks and caffeine. You guys saw the data last term. Energy drinks and caffeine. There's a paper, an incendiary paper written by a college student talking about how energy drinks need to be regulated more because the amount of caffeine is off the charts. I said, okay, that's interesting. And he was quoting numbers in his article. So I decided to do some research and dig them up. The numbers he was quoting were outliers. I got 500 or 700 different energy drinks, put them into a box plot, and as it turns out, the 75th percentile for energy drinks was less caffeine than a cup of coffee. Per the same, yes, 75th percentile for energy drinks. Per fluid ounce was less caffeine than a cup of coffee. So what the kid did in his report was he simply used the outlier data to prove his point. That's why I always check for them to see, is it legit to use them? Now, an interesting thing is the energy drinks had 14% of the data were actually outliers. So you had this box plot. Imagine the box plot, if you will. It looked like this. It looked like that. Because there were so many outliers to that, but still, more than 75% of them had less than a cup of coffee. But the ones that were outliers were like, one of them had, I think, it was a shot, an energy shot, and it was something like 400 milligrams of caffeine for the fluid ounce. Like, is that even legal? Can you do that? Well, I guess you can because it's sold. But so that's why I'm concerned with them, because mathematically they can alter the behavior. Oh God, I can get you the link if you want it. There's actually a caffeine monitoring website where they actually. Oh yeah, I tracked it down because I wanted to test this kid's data. I'm like, that doesn't. It's like the Jared Subway thing, right? Each Subway lose weight. I'm like, let's go look and see if you're actually using the right data. I can get you guys the link if you want it. But that's why I checked. No, it's a long answer to your great question. Okay. So it looks like they're doing better now. Errors are the same, aren't they? Right, except switch the sign. Except switch the sign. Here's the null. So type 1 would be, yeah, saying they're doing better, when in fact they're not doing better. That's your false positive. Type 2 would be saying they're not doing better, when in fact they are. Okay, and you guys put down whatever one you think is worse. It's up to you. You can have this. Well, that's the vote is for number 5. Which one do you think is worse in your own opinion and why? I predict I'm getting the same. I probably get the same results I got from last time. If you thought type 2 first, I probably think type 2 this time as well. That's totally fine. Totally fine. Your call on that one. Whatever you want to put. Now, once we get through step 5, we're like, okay, now test proper. Test proper. I'm going to come back to what Alan, Blake, and Nim were talking about earlier too. So let's go over to test to Santee. We got data, just adjust your data to where your frequencies are, which L1 is still the data. I put mine in L4 and L5. I don't know what you guys did. Did you just erase L2 and L3? That's fine too. I just stacked them on the end there. And then just switch the sign. Here's a kicker, right? It's tempting to just leave that sign in there. I am going to do that real quick to prove a point. I'm going to leave that sign less than to prove a point. And I'm going to turn these plots off. Okay, stat tests. Okay, I'm going to leave it less than and hit draw and let it do its thing. And if you do this, you're like, holy crap, there's a lot of area.
It's opposite.
Holy crap. Now, you don't necessarily know it's opposite right now until you realize what you told the TI to do. You put a less than sign in, but you were trying to test a greater than sign. That's why I have you write this down, honestly. That's the main reason. You very rarely see these hypotheses written out in symbolic form in research articles. But when you're learning how to run the test, it's really good to have them written out so you know what you're testing. Now the reason I like seeing this is, you got a test statistic at 2.0184. Guess what? That's still going to be the test statistic if you had the sign the right way. Because, remember, it landed over here. This is 0. And it's mu1 minus mu2 just like it was before. But now, who's bigger, mu1 or mu2? Now mu1's bigger because we're letting them use calculators and their average scores went up. So now you've got a positive test statistic at 2.01. That should be positive. The problem is you were trying to see if it was positive enough to be significant. But you told the TI to look if it was positive enough to not be significant. You see the problem there? So that's why if you get something like this, you can still learn something from it. That's a huge p-value. Now when I say huge, it's bigger than 95%. Which means that this little tail over here is less than 5%. If this is bigger than 5%, or bigger than 95%, mathematically this has to be less than. This is the Jeb Bush Florida helmet law all over again, if you put it in this way. Which means one of two things. You tested the wrong hypothesis, or you put the sign in wrong. So that's when you go, oh crap, I put the sign in wrong. I want to have this over here. So you're going to rerun the test with the correct sign. And again, that's the main reason I have you write the hypotheses out, is to make sure you put that sign in correctly. So I love what Emily said. I love what you said. Why don't you test the same thing? You totally can test the same thing. But then when you get that result, know what it means. It means you tested the backwards thing. Is that fair?
Yeah. To tell that it's just
raw data then?
It's a big p-value, but it's so big that it's opposite of what it should be. Because a big p-value doesn't mean you did something wrong. I mean, you guys saw a big p-value on the Ben AP pass rate. Big was 14% or 15% or something like that based on what you guys just showed me. That's big. If you flip that around, it's still going to be big. Right? So, it's, I mean, but it should... Sheldon, go ahead.
Go ahead.
No, go ahead, kick in.
Is there a better way to figure out which way to test it in the box, or a different way?
No, honestly, one of the reasons I like having a discussion in the last 3 weeks in class with you like this is because in reality, you come up with the research question. You collect the data, you make the graph, you decide who's doing better, and then you test it. See, when I tell you what research question to test, it's a little artificial because I'm doing the researcher's work for you as budgeting researchers. I want you to do that questioning too. So the question that I want you to think about is, okay, looking at those box plots, that one's to the right of this one's higher, is it significant?
So from the raw data, whoever pulls
Yes, ma'am.
forward
Yes, ma'am.
is what you...
Yes. So you pull that question from your own data. You may have a belief that the Core Plus kids are going to do better, but the data will tell you whether or not they are.
Is it okay to run the test and then decide to change?
Well, in that case, I would call that test run incorrectly, so you should have run it the other way. If you can change your sign, sure, because suppose you thought the Core Plus kids were doing worse and you didn't bother to carefully look at the data and you ran it the wrong way. Well then, absolutely run it again, because you're then going to be like, oh, you're not changing the data, and you're not changing confidence. You're not breaking the cardinal rules of statistics. You're just saying, oh crap, I put the wrong sign in. Fudging the data or changing confidence to make something significant, that that would not be cool. But that would be totally fine. What happened just then? You got so much area, you're like, oh my god, I'm looking at the wrong thing. I got the wrong hypothesis. Please, Blake, yeah.
Say that 4 plus is a placebo, and your population means are the same.
Mm-hmm.
Your test statistic is close to 0 and p is close to 50, or?
As long as you're doing a one-tail test, absolutely. Yes, so if Core Plus is placebo, which means it's a non-measure, well, placebo in...
They're the same.
So in other words, it's an ineffective placebo.
Yeah.
Yeah, I think you just what data set we're going to look at next, by the way. Thank you for that. So it's an ineffective placebo, which means that you come back with essentially the exact same area. But you have a belief that it's better. So what's going to happen is, you're going to have, let's just, we can draw it on this one. Here it is. You're going to have a test statistic close to 0, like you said, Blake. But let's say it's a smidge better, a smidge to the right. So it's a little positive, right? So instead of 2.01, it's 0.201 or something like that. You're then going to shade to the right of that. And it's going to go all the way in the tail, which is a huge p-value, close to 0.5. Exactly, close to 0.5. Which means you can't support that it's doing anything different. Even though it's a smidge higher, it's not any statistically significant higher.
And you would never flip it for the same reason.
The only reason I think it's okay to flip in this case is because it's clear you had the wrong hypothesis. Because the p-value was so humongous. If you flip that one, it's still not significant, is it? Mathematically, it's going to be 0.5 again-ish. Great question. Great follow-up, Shelby, and thank you guys for the discussion earlier with the 97%. That was fantastic. Good. So, back to what the sign should have been, which is that test statistic and 0.0231. Good. 2.3%? 0.02, call it 2%? Whatever you want to call it. 2%. It's less than 5%, yes? And that's what we use as a marker. So what's it look like? It appears it looks like the Core Plus kids are doing better as long as you let them use their technology. Which is kind of the point. If you teach them that mathematics with technology and then assess them without, that seems a little bit unfair. Now some people are going to argue, you gotta learn how to do stuff by hand. To which I say, okay, do linear regression by hand without using technology. To which case people will cringe and be like, okay, I give up. So you gotta, it becomes a more of a fundamental conversation. But this curriculum, once kids use technology, makes it part of the process, just like you guys do 44. So let them use technology, it looks like they're going to do better on the assessment. Could we be wrong? Of course. Type 1. Because you said something's different. You said something changed. You said Core Plus is better. You could be wrong, saying it's better when it's not. Good? Excellent. Question so far? We'll turn that one in, yes? Okay, good. Now Blake, you have given us the next data set we're going to look at. Because he mentioned the magic P word. is statistics. The one that's often used when I tell people I go to acupuncture. More templates? Yeah, plenty over here, for sure.